Hello and welcome to this new video where we discuss mathematics and physics on the board. In this video, we are going to use a strategy we used in a previous video to essentially derive the ground state energy of a harmonic oscillator, the quantum ground state energy of a harmonic oscillator, and we had only used essentially classical physics with some results that we had extended, if you will, to quantum mechanics. And the only aspect of quantum mechanics we had used is a notion of saturation of Heisenberg inequalities. Okay, and essentially that's when you take this thing and then you put an equal sign to so-called saturate Heisenberg inequalities. Now, what we are going to do today is precisely using the same strategy in order to obtain the ground state of the hydrogen atom. And we are going to see actually that this is a bit less trivial than when it comes to the harmonic oscillator. Okay, so let's look a bit at what we are looking at. So in general, we are looking at a system with a central potential. And this system is basically this one. Okay, so that's this one where you have a proton here and an electron there. And let's actually stay here. So you've got a proton and electron, and you've got a distance r between them. Okay, and the assumption here, contrary to the Bohr model, the assumption here is that the motion is going to be only radial. Okay, so we don't put any motion in the kind of the angular kind of direction. We are not looking at some sort of planetary system with some angular momentum there, so-called azimuthal angular momentum. Here we're only looking at a momentum and a coordinate which has to do with the radial direction. So in this context, we assume that the potential of interaction between the electron and proton is only dependent on the radial position, so on the radial coordinate here, the distance between the two. And so what we can do in that context is use the virial theorem that we had derived in a previous video. And so it says that twice the kinetic energy is equal to minus the actual potential energy in your system, okay, on average. Furthermore, the quantum part of it is the Heisenberg inequality. And again, what I mean here is that I need to talk about saturation, which is when you get an equal sign here. I'm using the a coordinate, and then it's conjugate momentum. And the coordinate here is a radial direction, and its corresponding momentum is called PR here. Then we need to remind ourselves from classical mechanics that the total energy of a system, the total mechanical energy, is the sum of the kinetic energy plus the potential energy. And finally here, I'm proposing a model for this hydrogen atom. So when I've got a proton here and an electron there, then what's going to be the model I'm looking for this particular problem of finding the ground state energy. So here I'm going to say that the kinetic energy, as I said earlier, there is no so-called azimuthal component to it, so there is no kind of orbiting part of it. So it's going to be simply PR squared over 2m. And then the potential is simply minus E squared over 4 pi epsilon 0 R, which is simply the Coulomb potential. So once we have that, essentially the goal is to combine these different expressions to inform essentially about what's going to happen, what kind of problems we are going to run into, and how quantum mechanics saves us from these problems. So what I'm going to do first is basically try to combine equation 1 with equation 3. So if I combine 1 and 3, then I'm going to get that the expectation value of the average of the energy is equal to the average of the kinetic energy plus the average of the potential energy. So here I put R. Let's put capital R because that's what I was using before. And so that's basically, I'm just taking the expectation value of equation 3. And then what I'm doing is that I'm going to use here the fact that it depends how you want to write it, but you can write it, you can write that Ke is equal to minus a half V of R, okay, and then plus V of R. And so it's equal to half of the expectation value of V of R. Okay, now what I'm going to do here, so that's what I get from combining 1 and 3. Okay, so 1 and 3 again were this and that. Now, if I substitute just in there the Coulomb potential, so now I'm adding 4, so I get that the expectation value of the energy is actually equal to a half of this quantity here. So that's times minus, and then I've got E squared, and then 4 pi epsilon 0 R, and obviously I need to take the expectation value of this stuff. Okay? Now, what do we notice here? The notion of ground state energy is that a system, in physics, a system tries to get into its lowest possible state of energy. Okay, so that's what mechanical systems do. That's what physical systems do. They go to their lowest energy possible. Okay. Now the problem with this, and that we didn't have when we were looking at a harmonic oscillator, is that here basically the lowest energy is when R is actually 0. Okay, this particular, if you look at this total energy here, you can plot that. Okay, so that's the expectation of that's the total energy, and that's as a function of R. And what you're going to see is that basically this thing, I should have drawn differently, but basically it's going to diverge and go to minus infinity as you're at 0. Okay. And so what that means here is that, and that was one of the problems that people put forward, is that essentially this diverges to minus infinity, and therefore there is never any kind of distance that makes the whole thing stable. Okay, and so the problem is that the electron apparently wants to collapse onto the proton. Even if you put some initial velocity, part of it is going to be radiated through cyclotron radiation, and so you can't escape basically this kind of minus infinity stuff. So then the problem is, how then do we solve the problem that apparently hydrogen atoms are stable? And so we need to justify that with this particular model. And so that's where essentially we get this part coming in, which is basically the Heisenberg inequality. So basically here we put 2, so Heisenberg inequalities, inequalities. So I just put that hi to the raise q, and so what we've got here is that we can't have all possible values of actually delta R and delta PR. They need to satisfy h bar over 2. Now, what I'm going to do here is 2 things. First, I'm going to start squaring these guys. Okay, so here this is h bar squared over 4. And then I'm going to define, that's really a definition here. I'm going to say that the expectation value of 1 over R is equal to 1 over A0. And A0 is what people call the Bohr radius. Okay? So that, I mean, for now, that's kind of it, okay? But that's not the end of it, because I'm going to say the following. I'm going to say that delta R squared and then delta PR squared, I'm going to say, and here this is an assumption, okay, that's an ansatz I'm actually putting here, that this is equal to 1 over 4, and then A0 squared, and then PR squared. And here I'm going to put, so the average of PR squared, okay? And you see the dimensions are the same. In terms of characteristic length, it makes sense because this is related to the expectation value of 1 over r. But basically here there is some aspect coming from the variance of PR that I'm relating here to the expectation value of PR squared. Okay, so there are multiple things that happen all at once, but basically that's what I'm asking. Then I'm asking the saturation of Heisenberg inequalities, so here. And so what I'm going to get is basically PR squared is equal to, and I've got h bar squared over 4, but I've got also 1 over 4 here. So I've got basically h bar squared over a naught squared. Okay? So now we obviously need to look at what are the equations that are left that we can use. And the equation we're left that we can use here is basically we are going to reuse again the virial theorem. And in that case, not in the general situation, but in the case where I'm going to substitute VR with this quantity. Okay, so next we are sub into 1. So I'm going to get P R squared over ME is equal to, so that's minus V of R, so that's minus, so that's E squared, and then 4 pi epsilon 0, and then here A naught, okay, because I'm taking the expectation value. So that's by using equation 1. Now I can substitute this expectation value by this one here. So this is going to be, this equation is also h bar squared over A naught squared, and then ME. And so what this gives us, let me check that you still have access to what I'm going to write. So if I combine these two equations, we actually get that A naught. So let's not get this wrong. So A naught is equal to h bar squared, so 4 pi epsilon 0 h bar squared divided by, and we have E squared, so ME times E squared. Okay? So that's our expression of the Bohr radius. Okay? So then what I do is basically I take this particular expression of the Bohr radius, and then I actually put it for the total energy that we've derived already here. So we have, let's call, for example, here, we call that, I'm not sure what to call that, but let's call that 5. Okay. And let's call that, well, let's call that 5, sorry, and let's call that 6. So basically, if I do 5, we are going to get the following. So this is minus a half, and then E squared, then 4 pi epsilon 0, and then A0. and then I need to substitute a 0 here. So I'm going to get minus a half, and then let's continue with e squared 4 pi epsilon 0, and then I need to substitute this. So I've got 4 pi epsilon 0 h bar squared, and then e squared me. So this gives us, it depends how you want to write it. You can get rid of some pi's here and there, and that's maybe what we are going to do by putting that h bar is equal to h over 2 pi. Okay, so you're going to get 4 pi squared, so that's 16 pi squared, and 16, you can say it's 4, yeah. So basically you're going to get here e to the power 4 me, and then here you're going to get a minus, and then 8 epsilon 0, and then h squared. Okay? E to the power 4 times me, and then divided by 8 epsilon 0 h squared, and this basically is the ground state energy. Of basically the hydrogen atom. Okay, so that's the idea, and you see that basically where this is coming from in this particular situation, where this is coming from is basically from here we ask the Heisenberg inequality to apply, and therefore delta R, or the radial position here, cannot be anything. It can't be as small as you want, because it's going to affect delta PR here. Okay, so basically that's how this works. You need to start with a few equations to start with, that most of them are classical. The only one that is quantum is this one. Then here we basically formulated the problem of the stability of the hydrogen atom. And then here we solved it by using the saturation of the Heisenberg inequality. And there is one aspect that has to do with like purely modeling in terms of quantitative modeling, and that's this one, where basically we assumed that this product of variance was equal to the product here of these averages with a factor here, a quarter. Now, in general, if you kind of don't know, then you can presume this thing with like some factor alpha that is of order 1, so does not depend on any of the parameters here, and then you would simply try to find that factor alpha experimentally. But here, basically, I've just put that it was a quarter. Okay, so basically that's it. That's how you would do it. No matter what what your background is, this is clearly much easier than solving the full Schrödinger equation and then actually put it to one state, etc. That's much simpler than the traditional way of doing it with the Schrödinger equation. So basically that's it. If you've got any questions or comments, by all means, do let me know in the comment section, and otherwise see you in the next video.